Well, good morning or good afternoon as the time zone indicates. Welcome everybody to our latest, our 12th Canadian Underground Infrastructure Innovation Centre Academy webinar. Today we're going to be looking at the City of Edmonton's Blatchford District Energy System. Being presented by Ruben Arellano, professional engineer, specializing in low carbon energy systems, specialist for associated engineering. CUIIC Academy is organized by the Canadian Underground Infrastructure Innovation Centre, University of Alberta, and Benjamin Media Incorporated. CUIIC Academy offers classes, courses, webinars, and events to help further underground infrastructure educational opportunities across Canada. The CUIIC Academy is going to be hosting several critical industry events next year. The 2024 Pipeline Rehabilitation Academy, which is happening March 13th and 14th in Richmond, and the 2024 CUIIC Advanced HDD School, which is April 24th and 25th at the Calgary TELUS Convention Centre in Calgary. If you want to learn more about these events, including registration, sponsorship, please visit us at academy.cuiic.ca. I'd like to thank and acknowledge MPipe for sponsoring the 2023 CUIIC Academy Webinar Series. Okay, on to the presentation here. Ruben Arellano is a low-carbon energy system specialist with Associated Engineering. He's based out of their Vancouver office, but he works with staff and clients in Associates offices and operations across Canada. He's a professional engineer with about over 20 years experience in a wide range of low-carbon energy sectors, including geoexchange, geothermal, biomass, wastewater heat recovery, district energy, and net zero buildings, ranging from large urban applications to unique remote and northern settings. He's always been active in industry, supporting various associations through committee, board, and chair roles. With that, I'm going to turn it over to Arellano and let you go from here. Thank you, Arellano.
Great, thank you. Just a quick audio checks, all good?
All good.
Okay, great, thank you. So thanks for the introduction and overview of the presentation. So I think as in the abstract, the City of Edmonton has established Blatchford Renewable Energy, which is a new city-owned utility created to achieve the long-term vision of Blatchford. Blatchford's a master planned sustainable community that will eventually be home to 30,000 or more residents in the heart of downtown Edmonton. And I'll be providing an overview of the innovative district energy sharing system from start, which was about 10 years ago, to construction and its current operation and future. Just briefly about Associated, you may or may not be familiar with everything that we do. We're 1,200 staff in 21 offices across Canada, and we have quite a range of multidisciplinary services. Most familiar probably with our municipal infrastructure, transportation, building services, water, wastewater. But we also have a low carbon energy practice, building services, mechanical, structural, electrical, asset management, environmental science, climate change mitigation, adaptation, and things like that. We've been around for over 75 years now, and we are a carbon neutral company committed to considering and implementing climate change mitigation and adaptation in all our projects. I'm going to give a few quick definitions because this topic and design uses a lot of common elements, but they're put together in perhaps ways that the broader community is not familiar with. So I just want to cover off some of the foundational pieces that go into making this low carbon energy system work. And the first, there's a lot of talk in order to decarbonize our building heating and cooling space is electrification. And the electrification usually is converting to using heat pumps instead of just combustion of fossil fuels or using electric resistance heat. Not always using heat pumps, but the majority of the applications are looking at that. And a heat pump is a simple mechanical device that uses the vapor compression refrigeration cycle, and it enables the moving of energy from one, say, lower temperature source to a higher temperature source. So in this example on the right side, our sources might be the air, so an air source heat pump, or the ground, which would be a ground source heat pump, or geothermal or geoexchange, or even waste heat recovery or wastewater heat recovery. And then just with some basic elemental examples, we might take 3 kilowatt hours of Earth energy, say, for example, from the Earth. The heat pump will use 1 kilowatt hour of electricity in order to operate, but it's moving that 3 kilowatt hours to a building space, and as a result, we have 4 kilowatt hours of heat in the building space. And that essentially is what we'd call a COP of 4, or a coefficient of performance of 4. In percentages, it's an efficiency of 400%, because we're using one unit of electricity to deliver 4 units of useful heat energy. Whereas in a typical combustion or resistance heating, you might have 1 unit of electricity or 1 unit of fossil fuel, and you're only going to get, 90, 98%, so 0.9 units of useful energy out of it. And on the load side, we can use this to provide heating. We can use it to provide hot water, process heat. And then the beauty of this mechanical device is that it can be reversed, so that we're taking the heat from the left side and delivering it into the ground as a sink, where you get an element of seasonal storage. So you actually end up using the ground as a sort of battery. So the same device provides both heating and cooling function. The next quick definition here is geoexchange heating and cooling, also referred to as geothermal, colloquially referred to as geothermal, ground source heat pumps, earth coupled heating, geoheat, all kinds of different terms. Often in the media, when you see reference to geothermal and they're talking about anything about buildings or district energy, they are referring to geothermal heat pumps or geoexchange. The geoexchange is simply using that heat pump that I described previously and coupling it with the earth to provide heating and cooling to buildings, either to an individual building or through district energy systems. It's using the relatively shallow earth, so drilling perhaps 300, 400, 500 feet deep. In Ontario, there's some innovations where they're getting down to 800 or 1,000 feet depth. But that's kind of the limitation. And we're accessing low-grade temperatures around 8 to 10, maybe 12 degrees Celsius in some cases. We're not talking about drilling, thousands of feet to get high-temperature geothermal energy. It's really about moving energy as opposed to combusting from a source. So you get very high efficiencies because you're taking earth energy and delivering it to buildings in the range of 300 to 500% efficient. And these systems, because they're typically water to water based and they're just using compressors, they have a very long life. They're low maintenance and they take up a lot less room in buildings, especially when you consider they're replacing a boiler system and perhaps a cooling tower system. Those are quite attractive in that sense. To just as an illustration here, the scale is not quite right, but it passes on the message here. So a building, you've got piping going from out of the building underground and connecting to a series of boreholes, and those boreholes are drilled into the earth, and they circulate a closed loop of fluid. So the fluid that's circulating in that pipe doesn't come into contact with the earth. It's strictly a closed loop circulation. I'll provide some more pictures about this later when I talk about Blatchford. Some images of a typical construction operation during the drilling processes and the headering processes. On the right side, this is actually in the bottom of a building excavation. So they're being installed underneath the building below the slab on grade for the parkade. And on the left, that's been drilled at surface. That's actually the Vancouver Airport project that we did recently. And then another definition here is just around wastewater heat recovery. So the concepts are similar to GeoExchange. It's using heat pumps to access a lower temperature source. In this case, it's the plentiful heat in wastewater flows, which can range from 10 to 25 degrees Celsius. And that heat is primarily, domestic hot water or processed water, clothes washing systems that heat energy you put into it and use very temporarily is literally just going down the drain and discharged to the environment after treatment. So we intercept that usually in larger trunk mains and pump the raw sewage out. And there's a couple of different systems that are available for dealing with the solids component of that. But essentially pulling that raw wastewater out, it goes through a screening system to remove the majority of the solids. And then it goes through a heat exchanger, and that heat exchanger will either go to a heat pump or can be used directly in the building application or district energy application. And then the solids as part of that screening system are coincidentally then returned back into the sewer main as part of that closed loop on the left-hand side. And then these technologies can be applied at a building scale, but what we're talking about here is in district energy. And so district energy is simply a centralization of an energy generation source, heating when we talk about district heating and cooling, and the distribution of that energy source to buildings. And this is a simplified schematic that's built off of the Blatchford model, but here we've got a GeoExchange field on the right side, an energy center, and then distribution piping to the buildings. The big benefit here is you get economies of scale with your more complex generation and operating equipment at the energy center. So you're able to scale up the more complex operations and maintenance, and you also enable accessing local heat sources. For example, if there's a wastewater heat recovery opportunity or process waste heat from an industrial facility or multiples of those, which are harder to access at an individual building scale. And then the other nice benefit of this as well is the simultaneous sharing of heating and cooling. So if you've got commercial buildings or offices or an ice plant, for example, an ice rink that's rejecting heat in cooling mode instead of it just going to the atmosphere and being lost, that heat is actually recovered and used as space heating in residential or in a pool application or something like that. So Now, regarding Blatchford. So, for those not familiar with the City of Edmonton, for many decades, it had a municipal airport, really right next to downtown Edmonton. This is an aerial view just before they decommissioned the airport on the left-hand side. And when they built the new international airport, there were some debates about what to do with that airport. Eventually, they decided to decommission the municipal airport, and it was closed in 2009. And at that point, the city had to decide what to do with the land, whether it would just be sold off to, standard land development, residential community development. But they decided they wanted to do something more ambitious and more leading in the world of sustainability. And council came up with this vision that Blatchford will be home to up to 30,000 Edmontonians living, working, and learning in a sustainable community that uses 100% renewable energy, is carbon neutral, significantly reduces its ecological footprint, and empowers residents to pursue a range of sustainable lifestyle. So this approach to a master planned community that has everything locally and integrated, sort of in contrast to a lot of typical sort of subdivision construction that we see to date. And that was in 2009. And in 2014, Associated was engaged to design a district energy system for the community. I'll talk a bit about that in the next slides. And the land development broke ground in 2015. And then the first phase of the district energy system was commissioned in November of 2019. And first residents had moved in 3 years ago, almost to this date in November of 2020. So that's kind of the short version of the timeline to date. The overall land parcel here is about 530 acres, and it has a 25 to, I think, 30-year full build-out for planned as part of the development plan. On the right, it's just a little bit of a planning level view layout of that area. So sort of more lower density townhome, stacked townhome type development. On the left-hand side, there's a town center with mixed commercial. I think there's a school in there somewhere, Civic Plaza. And then in the middle, there's a large park with 2 stormwater retention ponds. And I'm just going to show this quick video because animation and professionally produced videos can convey things a lot more succinctly and interestingly than us engineers can sometimes do in a PowerPoint. So if we can get this, I will click here. I will click here and launch and grab some popcorn and a couple minutes. We'll be back into the presentation.
Blatchford Renewable Energy is creating a sustainable future by delivering shared renewable energy through a district energy sharing system. This system delivers heating, hot water, and air conditioning in an environmentally friendly way. Sounds great, right? But how does it work? Let's start where it all begins, the sun. About half the sun's energy is absorbed into the Earth's surface as heat energy. This energy usually remains untapped. To access this renewable energy, we've built a geo-exchange field by drilling boreholes 150 meters into the Earth, where the temperature is always around 8 degrees Celsius, even in winter. This geo-exchange field is like a massive ground energy battery that charges the district energy sharing system. To capture this energy, we run a liquid that is colder than the ground temperature through the boreholes. Because heat always moves from hot to cold, the energy transfers from the warmer Earth into the cooler boreholes. This energy is now in the geo-exchange system, where it's pumped to the energy center. Here, a large heat pump works its energy efficiency magic. It only uses 1 unit of electricity to transfer 10 units of heat energy into the system. That's about 10 times more efficient than traditional systems. This heat energy leaves the energy center and travels to buildings through a network of underground pipes. Smaller heat pumps in the homes upgrade this energy one more time for heating and hot water. The really cool part is that the system can also provide air conditioning. This heating and cooling energy is shared between every building connected to the district energy sharing system. Here's an example. People living in one townhome are having a party. With all the extra people in the home, the temperature rises, so they turn the system to air conditioning mode. Meanwhile, people in the townhome next door are cold, so they turn the temperature up. A heat pump takes the excess heat energy from the first townhome and puts it back into the system, where it can then be used by the townhome needing heat. During certain times of the year, the community heating and cooling energy needs will balance each other out, so no new energy will have to be added to the system. Essentially, the entire neighborhood's heating and cooling needs will be met by recycled, shared energy. The system also shares energy between seasons. In summer, it can send excess heat back down the boreholes to be stored until it's needed in winter. Blatchford Renewable Energy's innovative system will provide environmentally friendly, reliable energy for generations to come.
And there we are. So hopefully that was a good overview, and I'll provide a little bit more detail given the time that we have here. So the just a couple of sort of schematic views of the district energy sharing system or district energy system. So on the right side is just a concept presentation of these sort of 6 energy centers that are envisioned to be built out over time, and they're done in these nodes that primarily share the local circuit of buildings, but they're also interconnected in order to share and balance out the overall energy distribution. The first phase, which is completed and in operation, is phase 1, which is highlighted on the left-hand side. And then over time, the subsequent phases will be built out basically in coordination with the development build out. Currently the total footprint, gross floor area for all conditioned spaces is 1.5 million square meters. So close to 15 million square feet, if I have my math correct, by 2040. And the total combined load for that is about 34 megawatts of heating and 46 megawatts of cooling on a peak basis. And these numbers, there's an ongoing sort of master planning exercise that has to be done. So along with the land development plan, year over year, as things change, technology changes, and building designs change, that can be adapted. But that's the current snapshot. It was conveyed, I think, pretty well in the video, but just to rehash that. So you've got the solar radiation from the sun, warming up the shallow Earth, which is kind of the primary source. It's not so much heat from the magma at the core of the Earth kind of energy. This is solar radiation that's collected in the ground. The geo-exchange ground loops that go 150 meters below ground collect that Earth energy. It's conveyed by header piping buried in the ground to the energy center. The energy center modulates that, sends it out at 10 degrees Celsius into the distribution piping system at number 5 here to all the buildings. And then the buildings have their own heat pumps to upgrade that to the usable, the space heating or cooling that's required in each building. And then either the warmed or cooled fluid goes back to the energy center, where it returns to the ground to be reheated or cooled again. The geo-exchange field, the land development management had the foresight to realize that the stormwater retention pond was an opportunity to install the field altogether below the stormwater management pond, so that it was sort of out of way, out of mind, and protected in the future, and you didn't have to try and complicate things by working it into land parcels or underneath buildings and that. So on the right side is an outline of the pond with 570 boreholes as the little dots laid out in a grid. And all those boreholes are piped together in a fairly complicated network. But essentially, hydraulically, we're trying to achieve equal flow through all of those borehole loops at once. So you have a series of header circuits, which are shown on the left, and they're piped in a reverse return arrangement designed to allow for efficient sort of low head loss pumping, while it being equalized through all the boreholes. And there's actually a couple of subheader vaults on the left side of the pond here. It's kind of hard to make out here, but basically those lateral headers all collect into a vault where there's another set of manifolds. So we only have, instead of having 570 pairs of pipes going to the energy center, we only have a single pair eventually of pipes going into the energy center. A couple of images of the field construction. So on the top left is the field before we got there and made a big mess. On the right is after the bulk excavation of the pond and the drill rigs getting started. And the bottom left is after most of the boreholes had been drilled, and you can see the trenches there for the shallow lateral piping. Bit of a gloomy picture. This was a summer when there was particularly bad forest fire smoke coming into Edmonton. So it was a little bit of an ironic scenario that we're putting in a renewable energy system, and our work was being impacted by climate change impacts from wildfires. And then the bottom right is just again a close-up of the drill rigs in operation. And after this is an image from, I believe, last year, after the pond has been restored, all the landscaping is completed. There's an effort here to make it look like as much of a natural, sort of ecologically friendly environment, in contrast to some of the standard stormwater management facilities that you see elsewhere in Edmonton and Alberta. And the geo-exchange field is underneath it, and there's no need to really ever go back. It's out of sight and protected as well from any future construction. At the top left there, you can see the energy center. I'll show it in some other images later. One aspect of geo-exchange, and I won't go into too much detail here, is it's very site specific. It depends on the local geology, what type of drilling systems are most conducive. And we do, a detailed look at the ground thermal properties. So there's some thermal properties testing that we do before the design as part of sort of pre-design feasibility work. And then during construction on the field of the size, we do some additional confirmatory testing to help update our thermal design models to what is a more representative set of thermal properties for the ground. So we're looking at temperatures, conductivity, thermal diffusivity as well. The first energy center, it currently has a 1 megawatt heat pump in it. It will be expanded. It's currently being expanded now to 3 megawatts. There's also full redundancy and peaking with natural gas boilers. This one was designed as a 2-story structure with a basement where the boilers and the circulating equipment is on the basement level, and the heat pumps and controls and maintenance are on the first floor. And there's also solar photovoltaics on the roof to help generate some of its own electricity. There's the finished product on the left-hand side. So, looking for some architecturally striking vision, and you'll see some even more audacious plans for future buildings and a little later on in the presentation. And the right side is the first heat pump that was installed, and that operation is being expanded or is in the works now for expansion. The distribution piping system, so that's collecting the approximately 10 degrees Celsius water from the energy center and distributing it through the streets into the buildings. This is all fusion welded high density polyethylene pipe. So very common, durable, long life piping system. The beginning part of the first phase is over 1 kilometer of the distribution piping system. So that's paired, so trench length over 1 kilometer, and it's up to 600 mil or 23 inch in diameter. And that sizing changes as it goes down the network. Eventually, the building takeoffs themselves are approximately 2-inch HDPE. Just a couple of sections. It's not, there's nothing too unusual that deviates from sort of more standard civil design here. The DPS or distribution piping system is buried at about 2.8 invert from existing grade. We do put frost shield insulation on top of it, but the pipe itself otherwise is not insulated, as you might see with some other types of district heating systems. And on the right side are the building service connections. Again, fairly standard with curb stops, and there's a temporary sort of flushing arrangements allowed, and then so that the builders can then later go and connect into the buildings. A large part of this is not just a technical design. You're establishing a utility that has a very close look at the financial model, the financial operation, viability, and sustainability of the operation. So along with the technical design, assessments, options analysis, we built a detailed financial model tailored specifically to the utility and the city's needs. And basically the key objective here was to develop a rate model that kept the customers' bills the same as they would have paid if they were otherwise outside of Blatchford. So they're not paying a premium for the district energy service. And so there's a lot of different angles here. A large aspect of a challenge with renewables is that it's a high capital investment. You're investing in assets upfront in order to recoup long-term operational savings and greenhouse gas reductions. But that creates a financing challenge, and with that cost of borrowing to cover during the beginning years. So there's a lot of focus and sophistication built into this. A couple of images today, which is actually February of last year, but again, aerial shots of what it looks like. On the left, that's looking south across the pond. You can barely make out the energy center there at the tip of it, and downtown Edmonton in the background. And then over to the right, and in the right images is the first the first elements of the land development, the streets, and the constructed homes for the first takers. I'm not going to get too much into the entire energy and GHG performance, but what we can just to illustrate kind of what happens here. So a typical townhouse outside of Blatchford might use about 37,000 kilowatt hours of energy a year. And in the yellow, you can see, the majority of that, 3/4 of it is natural gas for heating and hot water. And the other, 25% is electricity for plug loads. So your lighting, the other power sources inside your house. Now, with a system like Blatchford, the result is that we're reducing the actual energy consumption of those homes at the end of the day by almost 75%. So a reduction of 25,000 kilowatt hours. So a Blatchford typical townhouse uses 12,000 kilowatt hours the total energy use, but what you see is that the majority of that energy use now becomes the plug loads. So 75% of it is the plug loads, and only a quarter of the total is actually electricity used for heating and cooling. So their own heat pumps, and there's no natural gas being used for heating and hot water. So the result at the full scale is that that the community will emit 74% less greenhouse gases than a business as usual community outside of Blatchford. Future phases are going to include other energy technologies. The big one being wastewater heat recovery, and so pre-design or 30% design has been completed on this. The illustration there on the left of the wet well dry well is not current, but it kind of illustrates what's going on. So from an infrastructure point of view, the challenge here is that the sewers that we're tying into, the combined sewers, are over 17 meters deep. This is requiring a 22-meter deep wet well, dry well structure. The sewer is 2,400 millimeter diameter. It's also built in 1914, and so tying into that with new infrastructure in a safe and efficient manner is a challenge. The flows that potentially will be diverted from this is about 225 liters per second of wastewater, and that will provide approximately 10 megawatts of heat. It's a little bit different for their cooling, but it's 10 megawatts of heating and cooling. So this is envisioned for phase 2, and it will be a very large anchor renewable heating source, and eventually there will be also an additional geo-exchange field later on in the development timeline. The wastewater heat recovery facilities, so the phase 2 energy center, has got a very bold architectural vision, and I won't get into too much of what was being communicated here, but essentially the shape of the building on the right, the two sort of long structures are trying to convey the idea of the energy being exchanged from from the sewer flow going by, and then the energy being recovered on the right side of that. And this tall, large stack there for odor control and emissions flue is what you're seeing there as well. And then you can see from the 3D image the wet well dry well structure that I showed in the previous slide. The current status, so there's currently 71 homes connected, and they're looking at the sort of next sort of condo blocks coming online. In the next few years, they're expecting 390 accounts to be connected with 250,000 square meters of gross floor area by 2027. The first energy center, which had 1 megawatts of heat pumps, is being expanded to about 4 megawatts of heating and cooling capacity in the next year. And then that phase 2 with the wastewater heat recovery plant is looking to be added to come online in 2030. Currently, continuing the build-out planning with that modular, flexible, and phased approach that I showed in the earlier slides, and keeping that in line with the development planning, and adapting to any technological changes and advancements that may come along over the next 20 years. The feedback from the owner and operator is that operation is going extremely well, and that builders and customers are getting more confident with the idea of the district energy system and heat pumps, that there's a growing sense of appreciation in what the city is doing. On an energy basis, so far, it's provided about 1.2 million kilowatt hours of energy to those 71 homes since commissioning. And the last bit here is just there's been a lot of attention on this project. It's received a lot of awards. It's been and kind of humbling, I guess, in a way to see the attention. So, local awards from Consulting Engineers of Alberta, and home builders associations, and then at a national level, won the FCM Award for Sustainable Communities. The ACEC Canada Award last fall, we received the Engineering Award of Excellence and also a Tree for Life Special Achievement Award together, which was a first for us. And also the architectural design of the wastewater heat recovery plant won the Canadian Architect Award of Excellence last year. And then one of the more exciting ones is that this year we won from the Federation of International Consulting Engineers, or FIDIC. We won the 2023 Outstanding Project of the Year for Blatchford. So it's been quite an exciting couple of years on the awards front. And I know I've gone a little over the initial 20 minutes. I appreciate everyone that's still online, and we have some time here. I'm happy to answer any questions that you have.
All right. Thank you, Ruben. Very much appreciated. Very informative. And we have a number of questions here, so it's a great testament to the interest in this. For those of you who haven't, at the bottom of your screen there, you can ask any questions here, and we'll get to as many as we can. Let's just start at the top one here, very first one. What are the greatest challenges with aging infrastructure for geothermal energy exchange systems that you have seen or that you anticipate in the future as these systems age?
Interesting question. I mean, these owners are in it for the long term. So what do they look like when in it as they age? I think it's a positive. I mean, the HDPE pipe itself is warranted from the supplier for 50 years, but I mean, the actual longevity of it is far longer. I don't know how lots of people on the line can imagine how long buried, well-designed and well-tested HDPE pipe will last. So I don't know, we're through 100 years longer, I'm not sure, probably longer than the buildings are connected to. There's no other, it's a closed circuit. So it's not that you're dealing with, different fluids or mechanical systems that are buried underground. So it's highly resilient and long life. The heat pumps themselves are mechanical devices, of course. So, the reasonable life of a heat pump might be 20, 25 years. Again, what technology might come in the future, who knows? It seems reasonable that, maybe there's different types of heat pumps, but the ground loops will still be functional, and that's where the majority of your investment is. So the challenges in these systems is really there is some specialized knowledge in their operation, and there's some long-term monitoring that you want to do to ensure that you're sort of not overwarming or overcooling the ground. It's different than just a boiler that's taking an infinite source of energy from gas. So you are conceptually, you're generating your own energy on site. It's different than just taking a fuel that's generated elsewhere. Majority of energy comes from your own building. So it's really, it's sort of an operational optimization, I think is the challenge, but I would think that the infrastructure can last a long time.
Very cool. Thank you, Ruben. The question here, what is the average spacing between the boreholes?
So at Blatchford, the spacing, they're 6 meter spacings. It is very site dependent, based on on the load balance and other considerations. So there's some cases where they're as close together as 10 feet. We see a lot of 15 feet, 15 to 20 feet is quite common. If you've got as you go further north, or you've got only heating applications, you might start to see more like a 25-foot spacing to spread them out a little bit further. But 20 feet or 6 meters is a typical average.
Thank you. Next question here. What is the useful life of the system? We kind of touched on that with the first question, but here we go. Yeah.
So I guess there's two parts. I mean, the heat pumps life in our models is 20, 25 years. The ground loops 50 to 100 years. Yeah.
Cool. Thank you. And is there redundancy built into the energy center? What happens if the heat pump breaks down? Screen.
Yeah, so there's a number of levels of redundancy, and sometimes depends on the philosophy of the utility operator. What are they looking for N+1 at utility, and it varies. But conceptually, most geo-exchange heat pump systems, whether they're in a building or utility scale, will what we would call a hybrid system. They're going to have some kind of peaking with a boiler, because it's expensive and not cost effective in all cases to do 100% of your load with the heat pump. So there'll be a boiler as part of that. Now the boiler may just do a little peak, so it might just be a part load that's covered on the boiler side, or it might be, in this case, the city wanted full redundancy, so there's full capacity on boilers if all of the heat pumps should go down, which would be unusual, but that's what they wanted to demonstrate at this case. And also, in many systems, there's going to be multiple heat pumps. So when it gets up to 4 megawatts, we're talking about 3 heat pumps. So when one's out or one's in maintenance, you still have the other 2 in operation. And the other nice thing with a district system of this type that's got so much thermal mass in that distribution system is there's a certain amount of energy capacity it has for if there is a shorter term outage or something like that as well. So,
yeah, thank you. Next question. What are the cost comparisons between traditional energy systems like hydro, gas, or nuclear and these new low carbon ones? That's quite a question.
It's a big question. So, in terms of this topic presented here with Blatchford, the objective was that the customers would not pay any more than they would if they had lived outside of Blatchford. That was call it a philosophical mandate by the city. In the end, it's really comes down to a capital cost challenge with all those technologies. You're investing more in assets to have a lower operating cost over time in exchange for GHG emissions. That's kind of foundational to most renewables. And how when is the life cycle cost greater? So the way we have to look at this is to do a more honest life cycle cost accounting of the renewable system versus business as usual. And so if you're just strictly saying day one operating cost versus natural gas, which is super cheap, it may not look that great. But when you consider more longer term, depending on how you value greenhouse gas reductions, and in some cases what people are willing to pay, then it's different. So it's a hard one to summarize in one line. And every application, I guess the other part of that is every application is unique. What works for a subdivision in the Lower Mainland is different than what might work for a school in northern Alberta.
Yeah, difficult question. This might be fairly similar. A question in rough terms: what is the return on investment?
Yeah, that's a hard one to explain, and actually, truthfully, I'm not probably not privy to that level of. I mean, the financial model now is owned by the city. We set things up originally in the design, and they're since managing that. So it's probably not fair for me to try to answer it in simple terms, and I don't have a full picture on that right now.
Fair enough, and absolutely correct. Next question. What will be the temperature of the wastewater after the heat has been recovered, and where is that wastewater being disposed of?
Okay, good question. I don't know offhand what the temperature of the wastewater when it gets returned exactly. I can't recall what that is, but I do know that we look quite closely at the downstream impacts. So I guess first that wastewater is returned back into the same trunk, just downstream of where it's extracted from. So it's just in real time. It's just being circulated and returned back into the sewer flows. We do look quite closely that we're not adversely impacting the sewer flows themselves, not creating FOG impacts, and that we're not impacting adversely impacting the wastewater treatment plant downstream. So that is part of what's considered.
Okay, thank you. Next question. What fluid is used in the primary circuit, earth circuit?
I'm not sure which circuit, but I'll describe the ones that are there. So there's the circuit between the energy center and the ground loops. So that's a water-based fluid with propylene glycol freeze protection or antifreeze. So propylene glycol is a non-toxic kind of food grade additive as a freeze protection. The distribution piping system between the energy center and the buildings, it just has water only. There's no freeze protection required in that. And then within the buildings themselves, between the building's heat pump and the distribution would just be your standard HVAC design. Yeah.
Perfect. Thank you. All right, you got a lot of questions here. You must have had an amazing presentation. So awesome.
That's great.
What is the current procurement model for building out the DE system, piping, and other civil works? I'm
not sure that I can speak to that. I mean, I know that the first phase there was a pre-qualification round, an open pre-qualification round and tender process with a short list of proponents. But going forward, I can't say what the model is. Yeah.
Yeah. There you go. Okay. What sort of funding opportunities are available for heat recovery on large-scale projects?
Yeah. Good question. I mean, it varies but based on sector, geography, what government, what government's in place. But in general, what you have is in the private sector. So for either private buildings or private district energy systems. So there's a number of private utility companies out there, like CUIIC's and Creative Energies and Fortis's, Enwave. There's not really any funding provided to them other than what they have themselves, and there's also some low interest funding from the Canadian Infrastructure Bank tied to GHG reductions that they're accessing, and they also have some other incentives related to taxation that they can access. The bulk of the capital funding is geared towards different levels in the public sector. So remote communities, public buildings, rec centers, Indigenous communities, that kind of thing. And it does vary. It takes a lot to kind of navigate that funding landscape.
Yeah, I imagine. Excellent. Thank you. Probably have to be able to get to a couple more questions here, so my apologies on that. We're trying to finish by the top of the hour.
No worries.
How do you satisfy the different temperature needs between the various apartments of the same building? So, question.
So that's really an HVAC design question. Within the buildings, there's nothing really different than what we have in a quote unquote standard application. So the buildings, the current connected buildings are all fee simple townhomes. So they all have their own heat pump and their own climate control dedicated to the units. And in a multi-unit condo, they might either have a central heat pump that distributes to each of the units, and everybody's got their own controls through, a distributed water. They're probably not doing an air distribution system, but a water fan coil system, or they might have individual heat pumps in each suite as well. So there's quite a bit of flexibility for the builders on their approach. They just have to conform to connection requirements to the district system.
Cool. Thank you. A couple more questions here. Very kind of broad one here, but is there any potential accidents that could be catastrophic to the area? Fairly generic there. I think any catastrophic accident.
I mean, I guess I will. Not really. I mean, the drilling is relatively shallow. We're not talking about, I mean, in some areas for geo-exchange in the country, say in Ontario, they have to look for gas pockets when they're drilling. This is, standard for other types of drilling, environmental or geotechnical or oil and gas as well. In other places, we have to look for flowing artesian conditions as well during the drilling operation. But otherwise, I can't think of catastrophic accidents there might be. Yeah.
Okay. All right. Next question here is, what is the risk for wastewater dry wet well heat recovery when it comes to combustible gases being drawn into the loop and being compressed? Do you use specialized equipment for this application?
Good question. I will point out it's a highly multidisciplinary design, and there's a lot of specialists involved. I know that in the wet well, there is a lot of focus on ventilation, odor control systems for that in order to deal with gases. In terms of them separating out of that extraction system, I couldn't speak to that offhand. Yeah, interesting question.
Fair enough. Couple questions left here. All right. Wastewater is using sanitary water or stormwater, or is it mixed?
Yeah, the way it is a combined sewer. So it's quite, there's quite a cycle through the seasons. And we do have to analyze the sort of seasonal flows, both the volumes and temperatures, to identify sort of a consistent base load through the year that matches with the district energy demand.
All right, thank you. Oh, good. Last question here. I'm just going to quickly run through it. For the DE's distribution system, what considerations have been given to emergency response management? For example, if the water main breaks, needs to be dug up, are they going to hit your pipes, utilities, and what happens if the system has to be shut down?
Yeah, it's a good question. So each of the builders are free to put in what level of redundancy they want. I mean, it's a similar question, similar if you just got natural gas or electricity to buildings. So, gas main breaks or your power outage. So, risk and consideration that comes with cold climates that me and balmy Vancouver don't have to worry about so much. So there's not too much different from that perspective. If there are builders that are concerned about the level of safety from the distribution system, then they can put their own backup systems in as well. That the distribution system, I mean, there's a certain amount of redundancy in the way it's piped, and in that, there can be some looping, but at some point it starts to add a lot of infrastructure costs for fairly low risk. So the utility has to do a sort of risk management, risk analysis to see what they're comfortable with. But there is some, I guess, levels of, pardon me, redundancy and backup available.
All right. Well, first of all, great questions from everybody. Thank you very much for putting those out there, and great response from Ruben. Thank you very much for your presentation. Very thoughtful, well thought out system we have here, and it's interesting to see the innovation that's coming on board here. So again, thank you to everybody for attending, and especially to Ruben for presenting. I'd like to also thank all the CUIIC members that we have. You'll notice on the slide here, there's quite a large number of individuals that support us. And as well, I'd like to thank everybody on the call here, webinar, for attending. This is directly put on for everybody out there. If there's any more questions, feel free to send them out to us, and we'll see what we can do for you. But again, we'll be starting up again in January with some new webinars. And at that point in time, we'll send out some information on that. So again, thank you very much to Ruben. Appreciate your talk. And
my pleasure. Thank you.
End it here. Thank you very much.
Bye, everybody.